I'm looking forward to your talk, Khawla.
Hi, everyone. Can you hear me?
Yeah, we can hear you loud and
Great.
clear. Go ahead.
Thank you. So today I'm going to talk on the application of deep learning to mass spectrometry data classification. Our team is working on the development of accurate and rapid cancer and infection diagnosis pipelines. Mass spectrometry is perfect for such purposes since it provides no-targeted molecular information on the millisecond time scales. In addition, the recent advances in MS profiling enable its use for real-time diagnosis. So our motivation for this work comes from the fact that many real-world applications do not have access to large data sets because of data scarcity. In medicine, it is often the case that some samples are only accessible in limited amounts, which complicates the design of efficient classification models. So our objective for this work was to develop a rapid classification pipeline for cancer and infection diagnosis on small MS data by machine learning approaches. So here is the standard MS data classification pipeline with conventional algorithms such as SVM or random forest. Raw data must undergo pre-processing steps followed by a feature reduction phase. This pre-processing involves several interdependent steps, but its main limitation is that it is time-consuming. There are no golden standards for the optimal choice of parameters and for their quality evaluation. So all these factors lead to the fact that the standard pipeline is not adapted to a rapid analysis, while our approach is to use raw data directly for the machine learning step. So one of the algorithms able to do this are the convolutional neural network, or CNNs, because they offer various advantages over conventional algorithms, such as being efficient on raw data, which discards the need for pre-processing before the classification. The feature selection is integrated with the classification step, etc. But they also have a limitation, and maybe their main limitation is that they are data hungry, which means that they need to be trained on a very large data set to be efficient. So here, our small MS data sets we want to classify. The first one is a canine sarcoma data set, which contains 1 healthy and 11 different types of sarcoma. The second one is a human ovary data set, which contains a healthy and a cancer class. And the third one is a microorganism data set, which contains 5 pathogenic strains. So CNNs performed poorly for all these classification tasks, which was expected due to the low number of samples. So our alternative was to test what we call transfer learning. So transfer learning is a two-step process. A model is first trained on a large data set containing a large amount of data to extract an accurate representation. And this representation is then reused to build a new model based on small data set. So to apply the transfer learning, we used a data set acquired in a different biological context because the purpose of the study was to analyze the difference between a white and a gray matter in rat brain. Sizable gains in accuracy were obtained for all the datasets with the transfer learning compared to CNNs from scratch, which means that training a model with extracted feature even from an unrelated field is better than training the model from scratch when the dataset is small. For the 5-class microorganism, the classification was accurate, but we still need an improvement for the 2 cancer datasets, the canine sarcoma and the human ovary. So instead of doing a simple transfer from one source to one target dataset, what we propose to improve the classification is a new approach we called cumulative learning, which consists in training the same model through several classification tasks over various small datasets. So the CNN model was first pre-trained on the rat brain, then on the beef liver dataset, then on the microorganism dataset, before fine-tuning the EPAR parameters on the canine sarcoma dataset. On the other side, we trained the first the model on the rat brain, then on the second human ovary dataset before fine-tuning the parameters on our human ovary dataset we want to classify. So cumulative learning improved classification accuracy for both datasets, even when it is a low resolution dataset, as it is the case for the human ovary, and also for heterogeneous dataset, as it is the case for the canine sarcoma, because for some classes, samples were gathered from dogs at different ages and from different breeds. So to conclude this presentation, CNNs offer an end-to-end solution since they are efficient on raw MS data, which opens the door to develop rapid applications in the clinical domain. We showed for the first time that we can obtain an improvement of classification through successive phases of learning, which is an alternative when the number of samples is small. The principles demonstrated in this work could be beneficial to other domains where the training samples are scarce. We show also the diversity of tasks between datasets that didn't appear to share common feature, because the rat brain is a lipid dataset and the human ovary is a protein dataset. Also, among the novelties, we showed that the model was trained to predict only two classes, the white and the gray matter in the rat brain, and was efficient for classification in 2, 5, and even 12 classes. So just to finish, thanks to all my lab members involved in this project, and have you any questions?
Wow, thank you, Khawla. That was a really excellent talk. Lots of virtual applause. I really enjoyed it. We do have some questions from the audience. It's bringing up the chat, which is just finished. Come back to me, chat. Right, okay, so the question from the audience, from Natasha. You mentioned that CNN from scratch did not work well. What is the ideal percentage, or specifically, what is the cutoff percentage that you're looking for?
Yes, because here for simplicity, I showed only the accuracy, but we look also to other metrics such as specificity, the confusion matrix, etc. So in medicine, we are a little bit ambitious. So we want to obtain 100% accuracy, but it's not the case. So for us, obtaining above 98, let's say, it's a good cutoff for us.
Okay, awesome. So 98%, very high, but obviously the more the better. Another question from Noel. Could you explain the possible ways these classifiers could be used in the field? Who would you hope to use this in the end?
Our objective is to, because we are developing a real-time prototype with mass spectrometry. So the objective is to implement this type of algorithm to obtain in a rapid and maybe a real-time response when during, for example, a surgery, to be able to classify without doing, because as I showed in the first slide, the most common practice is to use anatomopathological examination of biopsy. But the problem with this type of practice, it is time consuming, because it will take between 30 and 40 minutes to get the result. It requires the presence of skilled pathologists, and it's difficult often to find what are the margin of the tumor. So the idea is to try to improve this type of algorithm, to be able to implement it in maybe new prototype for real-time diagnosis.
That's really interesting, and it would be an absolute game changer in the field of oncology, I'm sure. Yeah, very interesting. Lots of comments saying that they loved it. I just want one question. So it was really fascinating how you could train on large data of a very different type, and then use it to classify orders of another. My question is this a property specific to mass spectrometry data, or do you think it has applicability to other large data sets, say like genomic variation?
Yes, because what the next, our future work will be on the interpretation, because until now we have only a good accuracy as a metric for the having a good classification. But our next step is to work on the interpretation to find what region from the spectra is important during the classification. So why the model will classify this sample in this class or in this class. So the principle could be applied to other domains. And as I said, in medicine, we have often the problem of having small samples, especially if we are working on rare disease or rare cancer. Sometimes it's impossible to get more than 2 or 3 biopsies. So this is like a new methodology to be able to use CNNs with all their advantages, even if we have only small data available.
Wow, it is seriously exciting, and your passion for the work is clear. Thank you very much for presenting
Thank
here
you
today.
for having me.
Absolute pleasure. If we don't have any more questions, I think we can move on to the next talk.